Welcome back. We're in Projectiles worksheet number 3. Let's get into it. Cannonball is fired horizontally with a speed of 300 meters per second from the top of a cliff 75 meters high. Okay, cool. Let's draw it. Every one of these were drawn. You should be too. So here's the ground. I'm signifying that it's an immovable surface with these lines that are angled here, and I should be a little bit neater about that. Now it's fired horizontally, so that's a pretty important thing. So I position my cannon here so that it's firing out just straight horizontally and put a little stand on that. It's not too bad of a cannon. And we got a ball that comes out of this. Maybe make the ball not black. We have a ball that comes out of this, and the velocity is going straight that way at 300 meters per second. Great, from the top of a cliff. The cliff is 75 meters high, so that's a delta y there is equal to 75 meters. And up to there. And technically, it's like we're really going 75 meters high to where the cannonball shoots out of. If you want to be nice and technical, that's really what we're saying there. How long will it take the cannonball to strike the ground, the foot of the cliff? So I'm going to go and draw the general path that this thing is going to take. It's going to be some parabolic shape. At what distance from the foot of the cliff will it land? What is its range? Let's go ahead and do that in green there. Hold on 1 second. So that range there is going to be a delta x. Oh, I got to pause this. My thing's done. And so that delta x is right here, and so it's a question mark, but it's from the ending bit to the beginning bit right there. And what else are we trying to figure out? We're trying to figure out the velocity the instant before it strikes the ground. Well, I know that the velocity is going to be here, like tangent to its path, so that'll be the ending velocity looking something like that. And I don't know what that is. Notice I'll have to find the horizontal and vertical components there as well. So I'm going to go, I'll even put those in to remind myself that I need to figure out both of these guys. And I did those a little bit askew there, so I think that first one I made a little bit long. Maybe I'll make the vertical one. Try and get it right there. That's pretty close. And right there. So I don't know the green vector's velocity. Now I'm getting, why can't erase that? My eraser is like off from, there we go. So let me draw that back in. Sorry, this is getting all sorts of problems here on the first one here. And I also had thinking about, man, I don't know that angle there, theta, and that would be good to know that angle there. So let's go do that. Okay, so as normal, we split this up into the x dimension and the y dimension here as well. I'm going to give myself a little bit more room for the y dimension, as I usually have more calculations going on in there. I'll just pick one of these to start with, and it doesn't matter. A lot of times I start with the horizontal dimension for no particular reason. I don't know delta x, but that's okay. I'm trying to find it. I know the acceleration in the horizontal direction. Remember the horizontal direction. I go back up to my picture and go, yeah, I know that the ball anywhere along this path, the cannonball is being pulled straight down by the force of gravity. And we know that if it's being pulled down by gravity and only gravity, then it's going to be accelerating downwards, as we figured out in the last unit. And that acceleration is going to be negative 9.8 meters per second squared. And it's only negative because it's going downwards there. We know that the value of g is the positive version of that, but same idea. Okay, now that's in the x dimension, that's in the y dimension, but what about in the x dimension? Well, as always, we're assuming no air resistance here, so there seems to be nothing pushing against it left and right, which means that this acceleration right here, that acceleration is 0. 0 times any of that bit is 0. So that's just 0. Cool. The v naught t, well, we know the v naught that was given at the beginning there. And I don't know the time yet. Okay, so let's go ahead and let's put in, well, I'll keep it as variables there. So I know v naught, but I don't know time there. I know my v naught was this guy right here, and so I'll go ahead and put the v naught on there since it really is a original velocity there. So I can't solve that yet. I'm going to actually put it in the 300 meters per second right there. multiplied by time, just so I remind myself, because I'm going to have to come back to that. I got to remind myself I already know that 300 there. Okay, so I'm kind of stumped on the x dimension there, so I just go straight over to the y dimension, and maybe I can figure something out there. So in the y dimension, I get delta y is 1/2 at squared plus v naught t. Let's see if we can do anything with that. I know delta y. Okay, delta y is 75. Let me make little notes to myself. Sometimes I do this. I'll just make like little notes. Like I know that one's 75 meters. I know this acceleration is negative 9.8. I don't know the time. That's a question mark. I know the original, well, yeah, what is the original velocity? Is that 300 meters per second? Careful, because this is in the y dimension here. So at the beginning it's going horizontal, so it means it's not going vertical. So it's got 0 meters per second in the horizontal, or in the vertical dimension. And then I don't know time, but that's okay, because 0 times any time becomes 0. Okay, so let's simplify this then. So now I know that it's going to be delta y is equal to 1/2 at squared, and then plus 0. I know the second bit's going to be 0, so that simplifies this. And so now I go, hey, I know 75 for the y, and I know negative 9.8 for the acceleration. I can just use this to find the total amount of time that it takes to hit the ground. Now, if I figure out the total amount of time, look in the x dimension on the left side here, then I could just put that in and I'd find that. Okay, that's cool. Well, let me go solve this with variables. So I'm going to move the 2 over to the other side for delta y. I'll move the a over by dividing by a. And then I got the square that I got to take care of. So let me go ahead and take the square root of that. And that's going to be equal to my time there. Great. Grab my calculator. And that becomes pretty easy there. So 2 times my 75, so we know that's 150. You don't even need to punch that in. And then divided by my negative 9.8. And so now, let me write that out, because you might be saying to yourself, wait, that doesn't work. And I would agree with you right now. So let's that becomes 150 on the top over a negative 9.8 equals some time. And if you're looking at that mathematically, you're going, hey, that's going to give me an imaginary number, because I have a negative number underneath the radical sign here. What's going on? What gives? Well, we know that time's not going to be an imaginary number, because I've never measured that to be imaginary yet. So maybe we did something incorrect here. So let's look back up. We said that let's look at these 2 bits here. It's just acceleration and delta y. Well, my acceleration I know is negative because it's pointing straight down. My delta y we said is 75. Well, kind of. We know that the height of this thing is 75, but what is the ball, the cannonball itself, doing? It's going from way up here, way up high, down to way down low. Well, let's go ahead and let's call 0 meters my y position down here. That would mean that my y position up here is 75 meters. Not too surprising. Well, let's look at my delta y for the cannonball. The cannonball ends way down here at 0 minus the original was 75. And so the delta y for the cannonball, right? Delta y for the height of the cliff there is positive 75, because you're like measuring up. But now the cannonball is dropping down 75 meters. So sometimes, if you've already recognized these nuances here, sometimes when I go ahead and when I'm setting this problem up, I immediately put in the negative 75, recognizing that it's dropping down. I didn't do that because I wanted to point that out to you guys. So I recognize that the delta y is actually negative 75, and so then that becomes a negative 2 times 75, or 2 times negative 75, which is negative 150. And now that solves our problem there, so we get a positive value. And I get that the time is 3.91 seconds. Now you might say, isn't it plus or minus 3.91? And I'd say, absolutely. Well done on you, because we took the square root of something. But you know that it's not the negative, because it's going in the positive time direction there. So now, so the other one's extraneous. So now we just go and we plug that back in up there. And remember, I don't use the rounded value. I use that whole string of numbers there. And I'm going to go ahead and store that as letter T in my calculator, because maybe it'll come in handy later in this problem. And then I already have it stored. So I multiply that by 300, I get 1173.69, and that's in meters there, since those seconds are going to cancel out. And that's my delta x. Cool. So I figured out the horizontal range. I could even label that if I wanted to, but the delta x is the label for that. But just in case you're confused, that's my horizontal range. I'll put a box around that. That was one of the answers that they were looking for. All right, what else were we looking for up here? We were also looking for the velocity, the instant before it strikes the ground. Really, it's the instant that it's actually striking the ground, but let's not split hairs there. We'll have to find the horizontal and vertical components for this to do this. Well, let's do one at a time here. Let's do the horizontal bit first, because why not? Look at the horizontal bit. It starts at 300, and now what's happening in the horizontal dimension? Well, what's pushing and pulling on it in the horizontal dimension? Well, we didn't identify anything pushing or pulling out in the horizontal dimension because we don't have air resistance in any of these problems. It's accelerating in the vertical dimension, but how does that change the horizontal? That's right, they're independent from each other. And so, yeah, it's speeding up going down, but that doesn't change how it's moving left and right. So that means that all along here, my velocity in the horizontal dimension is staying 300, and so at the end there, my horizontal velocity is still 300. Cool, we got one of those figured out already. Let's go and see if we can figure out the other one, and the other one's in the y dimension. So I'm going to go ahead and I'm going to do that in the y dimension. Maybe I'll put another little break here, still in the y dimension, but just a break from those calculations. So now let's think about the velocity. Well, I got another handy dandy equation here, v is equal to at plus v naught. And we're looking for the ending velocity in the y dimension. We know the acceleration is negative 9.8. I know the time. Hey, cool. I just figured that was 3.91. And I have that stored in my calculator, so that's super handy. I'll put it in the meters per second squared there. Now, plus my original velocity in the vertical dimension. In the vertical dimension, it was just 0. So this becomes pretty easy here. So my ending velocity, and again, I'll put a subscript y on this just to remind myself that I truly am in the y dimension for that, is my negative 9.8 multiplied by that time. And I stored it in that time, I stored it in the calculator as t already, so I can just do alpha t times 9.8, negative 9.8, and I get right there. And so this is negative 38.34 meters per second. Remember, I'm using the whole string of values for the time, not the rounded bit. And I asked myself, what does this negative mean? Well, the negative means it's just pointing down, like we already drew that. So I'll go ahead and put that as the magnitude there. The magnitude is 38.34. I already have the direction as pointing straight down there, meters per second. Now, we're trying to figure out the total green vector there. And that green vector, is we can use Pythagorean theorem to be able to go and do that, since these two are at right angles from one another. And so let's go use the Pythagorean theorem. The ending velocity is going to be equal to the square root of the sum of the squares of those two. So the vx squared plus the vy squared, you might say. Just a shorthand, and now I'll just go put in those values there. So, whether you put the vy as negative or not doesn't matter, because you're squaring that anyways. I'm going to store that last vy as a letter in my calculator, and then that just makes punching this in way easier, because now I can do the square root of 300 squared plus my other letter. I just did it as a squared, and then in parentheses, and boom, it does it right for me. So I get 302.44 meters per second for my total velocity. Maybe I'll even put like total there just to remind myself that is not just the y, even though it kind of doing this in the y dimension over here. So maybe I should have separated these two and said, hey, this is not the y dimension anymore. That's actually something else. So it's v total, and I need to figure out what angle that's at. And so I'm going to use sine, cosine, or tangent. I'll go ahead and use I'm going to use tangent because why not? That's pretty easy. The tangent of theta is equal to the opposite side, which is the negative 38.34, and then divided by the adjacent side, which was 300. I do the inverse tangent to get theta by itself. And then I'm going to do inverse tangent, and I have that stored in my calculator. And punch that through. In this case, when I do it like this, I get the negative 77.28 degrees there. So I think about that and I go, hey, what does the negative mean? Well, I look back over my picture and I make sure that it makes sense. The negative, generally, in math class, means that you're measuring from the positive x axis there. Yeah, that's probably the best way to say that. And then measuring clockwise, which is the opposite way you normally measure that. And that's exactly what I have there. So, so that would be a good way to describe that. Cool. So that's it. We're done. So it's that V total at this angle right there. So like at maybe that angle. Yeah. And so that's let's reread the problem. Make sure I got everything here. We got the velocity. So how long would it take to strike the ground? Oh, that was actually I didn't actually put a box around that because I forgot that was actually one of my answers there. So yeah, we got that one, distance, and we got how fast. Cool. That's it. Have a wonderful day. See you. Bye.